this next test is really very much applicable in research. Like I said, I commonly use this one in when analyzing some data from my students or from the research. I mean, from their treatment of the data that they would ask me. Anyway, so much about this one. I'm talking about the so-called chi-square statistics. What is this chi-square statistics? Chi-square statistics is actually this statistics are this statistical test the degree of relationship between paired variables. Actually, there is also what we call one-way chi-square test, and there is two-way chi-square test. For one-way chi-square test, it's the same with the Anova one-way, wherein we try to only associate or try to look into one categorical variable. One thing that this is also, I mean, what makes this chi-square really helpful, it's because this is when we try to look for significant relationship between categorical variable. Categorical variable, for example, variables such as sex between male and female. And then there is a numerical data opposite to it as its dependent, example, dependent variable. So once you try to correlate that one and look for a significant relationship, then chi-square statistics is the best for us. Although, if it's only numerical data and then dichotomous categorical data on the other side of the variable, one variable is um, categorical and then the other one is, for instance, numerical. Since it's dichotomous, meaning to say two, we can use the point by serial correlation to see for the degree of association between the pair, between the sex and then the other variable. But on top of that, chi-square is still good. That is just an alternative or option. That is if you have a dichotomous data. But if it's already beyond dichotomous data, we can actually make use of chi-square statistics. Please do understand that chi-square will only work if your data set is normally distributed. Meaning to say, of course, we did discuss already what were the characteristics of a normal distribution. So one of which is having a bell-shaped curve. At the same time, uh, unimodal data, mean, median, mode are the same. Then the distribution is just scattered just within three standard deviation above and below the mean. Those were some of the characteristics of a normal distribution. And chi-square statistics is only applicable if your data set possesses the kind of those characteristics. In short, it's normal distributed. Otherwise, there are better non-parametric tests that you can apply. So chi-square is actually a parametric test. So, for instance, there is one research study from the College of Customs and Administration just this semester. They asked for my help. I mean, they tried to consult on me, and then I suggested Anova because I did not really look into the situation of the data set. And then since I was too busy to look for an external statistician, and then their statistician suggested that due to the fact that the data is not normally distributed, then we cannot use Anova, but rather the suggestion was they will use Kruskal-Wallis test, which is actually another statistical test. Kruskal-Wallis is actually a test used for still correlation, but for a data that is not normally distributed. Okay. Anyway, that is for chi-square. It should be normally distributed. It tests the degree of association, or it tests the whether association exists or relationship exists between variable. This is between categorical data and numerical data at the same time. Okay, so we did already. We have it already this way. The same with the common statistical test that we have. We will start with the degree of freedom. Of course, in this case, if it is one way chi-square, it's chi-square. Take note of that. It's not chi-square. One-way chi-square, the degree of freedom is basically k minus 1. Okay? Where your K here is the number of groups. Number of groups or groupings. So in this case, in chi-square statistics, we're trying to compare now the observed the observed no, the observed frequency to the expected frequency, whether um, they are related or not, whether it is right on point that the observed variable, the observed frequency is just right for the expected frequency. And then, yeah, that's it for the degree of freedom. So basically, what we're going to have here is k minus 1, where k is the number of groups. For instance, I have here f sub o and f sub e. O here is actually the frequency, this is the observed frequency. So it's the available data once gathered. Well, the expected frequency, that is the ideal. Remember the concept of critical value? For the critical value of any distribution, it's like in place already. That's the supposed that's the standard. And then what you're just going to do is that you compare the computed to the standard and try to see where do we go. But in this case here, we have the expected. So this is supposed to be expected on that particular using the y. Okay, so for example, you have three groups. One, group two, group three. And for example, I have here the observed frequency is 5, 9, 10. Then you have here the expected is 2, 3, 7, for instance. Now, if we will compute the degree of freedom for this one, it's basically how many groups were there? We have group 1, 2, and 3. So with that, we have three groups here. Our degree of freedom is simply 3 minus 1, giving us 2 as our degree of freedom. That is if it's one-way ANOVA. Okay? For a two-way ANOVA, two-way, for the two-way, no, for the two-way chi-square, our degree of freedom is computed like this. It's C minus 1 times R minus 1. See here is the number of columns there are, meaning to say the number of groups do you have. And then R here is the number of rows you have. Then you multiply. That is, the two-way ANOVA actually is applied whenever you have two or more categorical data, categorical variables involved. For example, if you're looking into um, sex, male and female, and then there are two, three uh, variables involved. For example, if you compare the level of um, the Likert scale 1 to 5 versus male and female, so somehow the degree of freedom is computed this way if you're going to impose chi-square statistics. Okay? So these are the two ways to compute the degree of freedom. Question. This is for the one-way chi-square and then the two-way chi-square. T minus 1 columns. And
Ah,
then
okay, sir.
this is number of okay, we have your number of columns, and then R here is the number of rows in your data set. Later, you will have an example of this one. Now, after we have the degree of freedom is, of course, our critical value. By the way, this is a symbol for chi-square. Chi-square critical, still we use the degree of freedom and then our alpha. We know our alpha in the conventional alpha that we have conventional alpha is 0.05. So in this case, if this is our alpha and then our degree of freedom is 2, what must be the chi-square critical? It's 5.991. That is our uh, chi-square critical. Well, the same, I will no longer stay long in the chi-square critical because it's very similar with how we... By the way, in chi-square statistics, we are using the chi-square distribution. The one that you have right now is the chi-square distribution. It's a distribution table for chi-square statistics. Okay, let's try to have this example in computing the chi-square, the computed chi-square. For the computed chi-square, this is our given formula. And let's have first this example. So we have FO, FE. Okay, so we have this example. And then to compute the chi-square for this one, our symbol is chi-square. So we have three groups here, and then assuming that there is only one computation or at least one variable here involved. So it's using now one-way Anova. One-way Anova. One-way chi-square. So again, with this particular example here, what must be our degree of freedom? The degree of freedom here is you have 3 minus 1 giving us 2. That's the degree of freedom. So in this case, what is our chi-square critical? So that is at 0.05 alpha, 0.05. So we have 5.991 or 5.99. Afterwards, to solve for this, by the way, our formula is the summation of x f sub o minus f sub e squared divided by f sub e. That is how we compute the, and take note the summation. This is actually, the summation here is from 1 up to k, where k is the number of groups. So in this case, there are three groups. So to solve for this one, this is eventually our frequency observation for the first group is 28. So that's 28 minus 24 squared divided by 24 plus you have 18 minus 16 squared divided by 16 plus 2 minus 8 squared divided by 8. Okay? Let's use our calculator to solve for our chi-square computed. Okay, we have our value as, what is the computed value? In two decimal places, our chi-square computed is 5.42. Now, if we try to compare the computed here and the critical, what must be the decision? Okay, this one falls on the acceptance region because looking at this one, you notice our null distribution is, by the way, our null distribution is actually having a longer tail here. You have to understand that this is our critical value of 5.99, while our computed is here, which is 5.42. So it falls on the acceptance region, as this is the acceptance region going here. This is the acceptance, accept. While this area here This is our rejection region. So you notice why our rejection region is focused only on the side, because remember, due to the squaring of value here, we will never have a result of negative, because the difference here between the frequency of the observation minus the frequency of the expected value squared it's always going to be positive. So there's no way that our chi-square value computed here will become negative. The only implication of the negative is that when in case the result here will be negative, it implies that the data is clustered near the mean. I mean, the data are actually spread, close to one another. And then on the other side, when the result is positive, then at least the distribution of data is quite spread. There is an additional note here, though, that if you are dealing with only two categorical categories, and your n, your sample size is not large enough, a more accurate value for chi-square computed is given by the Yates continuity correction. Yates continuity. So we can make a correction of our formula. So instead of having the formula this way, it will become chi-square is equal to the absolute value of f sub o minus f sub e, absolute value, minus 0.5 square divided by FE. Okay? So you notice there is a deduction here of zero point 0.5. This is called the Yates continuity correction. This is only applicable if you have two categories and then your n is not so large. There is no specific rule as to when do you consider n to be large, but rather, so long as it's not large enough. Okay, there is a specific ruling. This is precisely going to be in this same correction to the formula. So from this formula, if you wanted to apply its continuity of correction, then you can just impose this one. You notice our difference of the observed frequency and then um, expected frequency. They are within an absolute value symbol because this implies that the result of this will always going to be positive. Okay, but still it is in summation form. Okay, it's still in summation form. For instance, imagine that a developmental psychologist is studying color preference in toddlers. Each child is told that he or she can take one toy out of four that are offered. So there are four toys of different colors offered to them. Then the toddler can only pick one. That is the instruction. So this is color preference for the toddlers. So the recording is like this. Okay, there are four colors. We have red, blue, yellow, and green. And then we have the actual observation, and then we have the expected frequency. Now for the 40 kids involved, so there your n here is 40. For there are only 40 toddlers involved. For the 40 toddlers, 13 of them selected red color, the red color of toy. Then there were 9 selected yellow, 15, 9 selected blue, and 15 for yellow. And then lastly, we have 3 for color green. Now, the what they call this one, the expected frequency here is somewhat easy to identify. That depends upon our null hypothesis. In the event that our null hypothesis is stated as there is no color preference in toddlers for the toys, so that means to say all the respondents will be equally distributed to all in the frequency expected. So if there are 40, so we'll now assign 10 per color as expected. So meaning to say we're expecting that 10 of the respondents or 10 of the toddlers will select red, 10 will select blue, 10 will also select yellow, and 10 for green. That is if our null hypothesis stated that the toddler there has no, I mean, the toddler do not have a color preference. After all, this test here, the psychologist is doing is knowing whether toddlers have a color preference for the toys that they have. So if you look at this one now, we have the situation. So what is the degree of freedom here? Our degree of freedom is going to be 4 minus 1, which is 3. What is our chi-square critical? Our chi-square critical is, okay, it is 7.81. That's our, and then let's have our chi-square computed. So that's going to be 13 minus 1, 13 minus 10 square divided by 10. Okay? We're not applying any correction here. We're not applying the yields correction. So we will just use as is for the formula. Only when there is instruction that to adjust the result and we can disregard some of the, I mean, we can minimize the correction or the error to be applied, then we will apply the yields correction, which is we subtracted zero point 0.5 from the numerator plus 9 minus 10 squared divided by 10 plus 3 minus 10 squared divided by 10. What is our chi-square value computed? I forget one. It should be this plus 15 minus 10 squared divided by 10. So that's going to be, our answer is 84.4. This is the computed. So if comparing this one and this one, our decision is reject. So if we're going to look at the distribution for that, it's like this. This is 7.81. So happened that 8.4 is here. So it landed in the rejection. So in this case, since the null hypothesis says that there is no color preference for among toddlers, it turns out that we rejected the null, means to say that toddlers do have a color preference for their toys based on this data gathered and then based on the computation. Okay? So with that decision, we reject the null hypothesis. It means to say the result is significant. There is a significant relationship between uh, toddlers' preference of color and then toys. Since we rejected the null hypothesis at 5% level of significance. Okay, the one-way chi-square test is also known as or referred as the goodness of fit test. This is labeled especially when the emphasis is that the emphasis of the test is on measuring the fit between observed frequency and the frequency predicted. Okay, by a theory or hypothesized population distribution. So that is one way. This one is also known as the goodness of fit tests. Okay, later on we will have the two-way chi-square tests. By the way, before I'll move forward, any question from here? Can I have someone to read the problem?
A soft drink manufacturer is conducting a blind taste test to compare its best-selling product, X, with two leading competitors, Y and Z. Each subject tastes all three and selects the one that tastes best to him or her. A. What is the appropriate null hypothesis for this study? If 27 subjects prefer product X, 15 prefer product Y, and 24 prefer product Z, can you reject the null hypothesis at the 0.05 level?
Okay. So the question here, there are three questions. First is what is the appropriate null hypothesis? And then afterwards is whether we will reject the null hypothesis at 5% level of significance. So first, answering letter A. What do you think is the appropriate null hypothesis for this one? Null. Take note that the soft drink series is trying to conduct a blind taste test to compare its best-selling product X with two leading competitors Y and Z. So, how do you intend to state the null hypothesis in this one? It is somehow like that, but I'd rather we will no longer use symbol. In fact, the book do not encourage symbol anymore in this one, but rather we will have the statement here. For the null hypothesis, we just simply say that uh, all three in the taste test to compare the best-selling product. So we can state the hypothesis that all three soft drinks have the same taste. So in other words, there is no alteration whether which tests have a greater or have a better taste over the other. So in other words, okay. So again, null hypothesis here is that all three tastes are just the same. So in other words, uh, brand XYZ have the same tastes. Okay, and then for the alternative hypothesis, since the soft drinks manufacturer would like to know know about comparing their best-selling product, soft drinks, over the two leading brand as well, competitors. So we will then say that the alternative hypothesis that there is a significant difference, or in other words, that all three soft drinks are not having the same tastes. Okay, so there's an alteration on the test, on their taste tests of the soft drinks. So with that saying, we will just record first. Okay, we have our observed frequency and then of course our expected frequency. Then we have here brand X, brand Y, and brand Z. And brand X, the observed frequency was 25. And then for brand Y, X rather, brand Y is 15. And then brand Z is 24. For the expected observation, take note that all respondents have tasted all the three. I mean, tasted this one, all in all. So they tasted the soft drinks X, Y, and Z. And then they had to choose one, which one is the best for them. So 25 of them responded that brand X is tastier. And then 15 responded Y is better, more tasteful over the two other brands. And then 24 said that brand X is uh, much better in terms of taste. So looking at this one, how do we decide now our expected value? For the expected value here, based on the null hypothesis that says there is no alteration, that all three brands, um, all three soft drinks are just the same in terms of taste. So with that, we would now assume that all the three, since they are just having the same taste, so all the three will receive the same number of respondent. Okay, so the expected value for all the three are just or must be the same. So how do we do that one? We don't know the total. We don't know our n. What is our n here? What is our df? And what is our chi-square creep? Later, this is in preparation in answering question letter D. Now, we don't know our n. But if you will read the problem between the lines, it says that all respondents were asked to taste all three soft drinks. And then they'll have to pick one. So to get our end there, we just have to add all of this because all of this actually have tasted uh, the three brands. So we've got 15, 45, we have 64, 15,
Sir, excuse me, sir. Kanang 25 sa X, sir. Baka dili na 27.
I sure
Dili
it's
na.
27. So we have 27, 15, 24. So that is going to be
66.
49. So we have 66 is our n. Now 66, and take note, our expected value must have the same number as us. So this must be divided into 3 for there are 3 brands. So giving us now a result of 22 for each expected value. So we're expecting to have 22 who will be selecting brand X, 22 will be selecting brand Y, and 22 selecting Z. Assuming now that since our null hypothesis was stated that there is no alteration and in terms of taste for the 3 brands. So meaning to say, if that's the case, as expected, each brand will have I mean, each brand will have the same, or brands will have the same amount of responded as expected. All of them, or they have an equal number of uh, respondents who will be selecting these brands. So we have 22, 22, 22. Okay? Any questions so far in how I did set up the table? So in this case, the null hypothesis for letter A answer is that uh, there is no significant, wait, all three brands are, I mean, all three brands stays the same. Okay, and then the alternative here is that um, all three brands do not have the same taste. Okay, as there is alteration. So that means to say if there's alteration there, we can significantly consider now that maybe brand X is better, or at least what we can find it doing well compared to the rest. Okay, so we have it in this form now. In this case, what is our degree of freedom? Let this deal 3 minus 1 equals 2, right? For there are three groups. And then our T critical is still 5.99. Okay, now let us have our computed X or chi-square critical. So that's chi-square. We have 27 minus 22 square divided by 22 plus 15 minus 22 square divided by 22 plus 24 minus 22 square divided by 22. Okay, so in this situation now, we just have to solve for this to answer the question whether we can reject the null hypothesis at 5% level of significance. So you have 27 minutes, that's 525 divided by 22 plus 49 divided by 22 plus 24 4 divided by 22. So we have the result here is 3.54. 3.50 55 actually. So if you look at this result now, comparing the critical and then the computed is less than the critical, so it falls on the acceptance region. Therefore, we fail to reject the null hypothesis, claiming that there is a significant difference between the taste of. We fail to reject the claim that all three soft drinks have the same taste. So, in other words, based on the data gathered, based on these results from the 40 respondents, we cannot, I mean, statistically, we don't have sufficient evidence to say that there is an alteration when it comes to the taste of the three soft drinks. Okay? As the test of hypothesis, or the test here comparing the critical and then the computed landed in the rejection region. So we fail to reject the claim that there is, I mean, that all three saw the taste the same. Okay, now we will have the next is we have the two variable contingency table. For two variable contingency table, it's actually a 2 by 2, a 2 by 2 table. Meaning to say there are two variables involved here, and there are also two groups or two variables row and column wise. Okay, most of here is the instance. Most of the interesting questions in psychological research involve the relationship between at least two variables rather than distribution of only one variable. The first example I gave you is a distribution of one variable only, which is about uh, the soft drinks. But in accordingly in the field of psychology, we're more, or it's more common to have a variable of two by two variables involved. So for example, sex, male, female, versus the example, there is a study that presented to me the other day that There is um, their mobile attachment, their level of mobile attachment, and then the other one is their social anxiety versus. So that means to say, if it's like this, male female versus mobile attachment and social anxiety, then we are going to look at this one whether the data is significant or not, whether there is a significant relationship between the gender or the sex of the respondent, the participants, versus their level of anxiety, social anxiety, and mobile attachment. Okay. For instance, suppose a researcher believed that the adults whose parents were divorced are more likely to get divorced themselves compared to adults whose parents never divorced. We cannot quantify the degree of divorce, okay? We cannot quantify the degree of divorce because it's either divorce or not divorce only. So we cannot count it as the one is divorced, two is not divorced. We cannot do that one, and rather we can just only consider divorce and not divorce as one of the variable, the categorical variable. And then the other categorical variable is that whether they will also get divorced or not divorced if they were actually came from a family that were also who were also a byproduct of divorce. Okay, to simplify the problem, we will focus on the female members of each couple. Suppose that the parents were divorced before the subject was 18 years old, and 20 parents were married until the subject was at least 18 years old. Half of the 30 women in this hypothetical study have gone through their own divorce. The other half are still married for the first time. To know whether the divorce of a person's parents makes the person more likely to divorce, we need to see the breakdown in each category. That is how we currently divorced women can be broken. So we will look at this one. This is the presentation on the table. Actually, the row sum here is associated because later on in the two-way testing of null hypothesis is we are going to consider the row sum and then the row column for the expected frequency. So this one is the kids here self-divorced. They got divorced as their parents were divorced before 18. So we're trying to look at this one. So it's like seven seven of the total women tested that their parents when their parents got divorced before they reached 18, and they happens to be divorced also, got divorced also in their own marriage. And then three of those respondents, female respondent, whose parents were divorced and self-married, married, means that they're still married as of the moment and never got divorced. For parents who were married, the female respondent whose parents were still married got divorced, 8 of them. And then who were still married is 12. Now what we can do, we'll get the sum column, we'll get the summation which is 10. The summation of this one which is 8, 12, this 20. And then towards there, the row column, this is 15. This is also 15. Okay? And then our sum total here, we have 30. This is our N, 30. So meaning to say there are 30 respondents all in all. Okay. So with this one, now we have this information. This is an example of a 2x2 contingency or a contingency table. It is cross classification. So you notice there are two here. Then there are also two variables here. There are two. Then we have a 2x2 categorical data. Categorical data, it's because our category is parents divorced, parents married, self-divorced, self-married. So we cannot actually quantify this one. We can only count how many were there, but we cannot assign number to self-divorced and self-married. We can use coding of 1, 2, but the 1 and 2 there does not have meaning at all, but rather they were just a classification for those who were self-divorced and self-married. Okay? That's the instance here. So what's the point of us discussing about the contingency table? Okay. The data in such table are often referred as the cross-classified categorical data. Cross-classified, it's because we're just going to simply do a cross. We will have a separate computation for this one. For if we will have a contingency table, the computation for the chi-square, let's compute the, let's have the computed chi-square for this one. Okay, there is actually a simpler, a separate formula for chi-square. It's like this. Since it's a 2 by 2 or it's a contingency table, meaning to say we have a 2 by 2 categorical data. We have chi-square is simply this one, n times AD minus BC square divided by A plus B, C plus D
Excuse me, sir. Ang kana
times
nga example, sir, kaysa
AC. For a while, let me finish first. B plus D. Yes, what's your question?
ang kana nga example, sir, ba kaysa two-way kay square sige hapon na siya, sir, no?
No, this is kind of special two-way chi-square because we have here a 2 by 2 contingents, meaning to say we have a 2 by 2 categorical data, which is this one here and then the 2 here. So somehow we can modify the two-way chi-square statistics to a different formula such as like this. Now, how do we compute? It's like first, and our n is 30, and then AD, this is A, B, C, then D. Then this is our D. So we have AD. Meaning to say we will multiply now 7 times 12. We got 84 minus 24. And then square. Then for the denominator, A plus B. So that is 7 plus 8 times 3 plus 12 times AC. 7 times, 7 plus 3. Then you have 8 plus 12. Which if we will compute this one, the result will be, that is 84 minus 24 square times 30 divided by this one. This is 7 plus 8, that's 15 times, let's 15 times 15 times 10 times 20. We have 2.4 as our value here. This is our computed value. Well, this is only applicable if it is a contingency table, meaning to say we have a 2 by 2 categorical data. So that's 2.4. The example, if we will remove this data here, example, that's the only one that we have. We have categorical here, then we have number here. More or less, we can have the point. We can use the point by serial correlation to know whether association exists between a categorical data, dichotomous categorical data. But in this case, it's a 2 by 2 contingency. That's why we can modify the two-way chi-square into this particular formula. So have it in this form. Compare this to the critical. By the way, what's the degree of freedom here? DF. So we have here the degree of freedom is 1. If alpha is 0.5, but this is the critical value. Okay, 3.84. So that means to say it is insignificant. In other words, looking into the situation whether what more likely will happen? Those who are, I mean, women who were actually, uh, their parents were actually separated and then not separated, whether it is related to them being uh, divorced also in their own marriage life, there is no, based on the data, there is no sufficient evidence that that is possible because we were able to reject null hypothesis. The null hypothesis is telling here is that uh, the test here is that women who are women who are women whose parents were divorced before 18 years old were more likely be will be divorced themselves also when they'll get married when they'll marry someone. That is the claim. And the alternative, I mean the null hypothesis says that there is no significant relationship between women whose parents were divorced, that they will most likely will get divorced themselves as well. But since we cannot reject, or we did not reject the hypothesis at 5% level of significance, it follows that the claim now that if they were the woman who were actually having parents who were divorced, does not imply that they themselves will also get divorced when they will get married. Okay, that is the implication of the result here. Degree of since our computed value is 2.4, which is actually less than our critical value, that is 3 point something. I forgot what is that something.
Sir, if ang Z critical, sir, is greater than Z computed, then i-accept siya, sir.
It's the same ruling. If
Okay,
the
sir.
if the critical value is less than the computed, then reject the null. Otherwise, accept or fail to reject. I'll just incorporate this right away because I may not touch this anymore. In the case of 2 by 2 contingency table, the one that we have, there is a very natural choice for a measure of association. Pearson's R, if we may recall, Pearson's R has actually a scale or ranges of Pearson's R value to identify the degree or the strength of correlation. Remember when we did last time, like for example, what's that? When we have, okay, so in Pearson's R, depending on the value of our Pearson's coefficient, we would know the strength of association there is. Remember? Now the same also for contingency table, we can also know the strength of the association by a certain computation, but not for chi-square value, but rather using the phi coefficient. Phi as in Greek letter phi coefficient. So with our phi is computed as phi equals the square root of the chi-square computed divided by n. So in this case, what is our result here? We fail to reject the null. So meaning to say there is no association at all. But for the purpose of computation here, our chi-square is 2.4 divided by 30 is our n. Get the square root. What is our phi value? This is what I mentioned earlier. The two levels of grouping variable can be assigned and any two values 0 and 1 and the most convenient. And the ordinary correlation formula can be applied. The result is often called the point biserial correlation. That's the R sub PB, the point biserial correlation. As a reminder that one of the variable has only two values and that is the sign of the correlation probably irrelevant. A similar procedure can be applied at 2 by 2 contingents table. In this case, both variables are dichotomous. Remember, this is 2, this is 2. That's why it's both dichotomous. But for the point biserial, the two levels of grouping variables can be assigned by two values, has only two values, and that sign of the correlation is probably irrelevant. For the point biserial, this is 2 here and then versus 1. It's like this. This is the biserial. But since it's already 2, 2 here, that's why we use the contingency table. And thus to know the the strength of the association, then we can actually use here the phi, which is 0.28. Now, how do we interpret the 0.28 for a while? It's also the phi coefficient is also known as the four-fold point correlation. The phi is also known as the four-fold point correlation. This is in relation to the point biserial correlation. Okay. Ay, sorry. It says here, the person that the phi is interpreted as considered as a medium effect size as it is close to 0.3. Recall that zero point 0.1 would be considered as small and zero point 0.5 is large. So in this case, since this is our value, this is the roughly the very quick interpretation. 0.1 is considered a small effect. So the degree of association here is small effect, and then 0.3 is medium, and then 0.5 is large effect. That is the interpretation of the phi value. Since 0.28 is very close to this value 0.3, which is that's why it implies that there is a medium effect or there is a medium strength of association for this result. But by the way, in an actual statistical, in an actual research, we will no longer test the strength of the association if our interpretation of the result is not significant. Because what's the point of finding the strength of the association when, from the first place, the variables are not related? Okay. Remember, in shortly saying that in our test, we test whether the variables are related to one another. If they are related, that's the time we will look into the strength of their association or relationship. That's where the phi comes in. But in the event that our association is not significant, so there is no point of knowing whether what is the strength of the association, because in the first place, the association is not significant. Did you get me? That is the same is true also for the two-way Anova, two-way chi-square. For instance, in the diverse example, okay, this example, you can assign one for divorce, okay, one for divorce, and then two, a zero for not divorce for both parents and self. In that case, a positive correlation would indicate a tendency for greater divorce among those whose parents are divorced, and a negative correlation would indicate the opposite tendency. The sign of the phi coefficient becomes irrelevant, though when the strength of association is measured by squaring, you may recall that squaring a correlation coefficient is useful because it tells you the proportion of the variance accounted for. Squaring phi gives you an analogous measure squaring both sides for formula. Anyway, that's no longer relevant. On the other hand, there is what we call also the Kramer's phi, also known as the Kramer's V. But before I'll discuss the Kramer's V, I'll still have to run through with the 6 steps because this time we're going to have now a two-way chi-square test, but not a contingency table, okay, or a 2x2 contingency. This is a 2x2 contingency. Now, what I'm talking about here is that we will have two versus three, or two or more categorical data versus two or more categorical data, not just 2x2. Because if it's 2 by 2, then we're doing, in this example, the contingency table. Okay? What I'm going to do now is we'll share to you some instance and then we will work with this one. You have to pay attention carefully to these details here because this one is the actual test of hypothesis. By the way, there is also a note that the one-way chi-square statistics is barely used in doing statistical research. I mean, in doing statistical analysis of data, especially in research, is because uh, it's not more likely to happen. We don't intend to compare, look for a significant association of, in short, it's not uh, mostly used. What is mostly used is that we have two or more categorical data that is being compared. Okay? Anyway, that means to say we're going to focus our attention to two-way chi-square tests. Let's look at this instance or example. Okay, we will follow the six steps of null hypothesis testing. Okay, I'm gonna show you share to you the question, and then we will perform the test hypothesis here. Can I have someone? Can you read the problem, Alon? I'll share it first. There. Can you read the problem, Alon?
Imagine that a psychiatrist has been frustrated in her attempts to help chronic schizophrenics. She designs an experiment to test four therapeutic approaches to see if any treatment is better than the others for improving the lives of her patients. The four treatments are intense individual psychodynamic therapy, constant unconditional positive regard, and Rogerian therapy, extensive group therapy and social skills training, and a token economy system. The dependent variable is the patient's improvement over a 6-month period, measured in terms of three categories: became less schizophrenic, improved; became more schizophrenic, got worse; or showed no change. The different proportions of improvement among these four treatments can be tested for significance with the usual 6 steps procedure.
Okay, so there you go. Again, we are testing here. There are two variables involved. Um, there, whether they have improved in terms of improvement, three categories. This is 3 versus 4. So we can no longer apply the 2 by 2 contingency because that's just 2 versus 2. This time we have 3 versus 4. Here we have the first categorical data involves three categories, which is uh, less schizophrenic, more schizophrenic, and show no changes. Those were the three categories. And then the other four categories in column, we have the four types of therapies employed. First is we have the psychodynamic therapy. Second is the constant and conditional positive regard and Rogerian therapy, or in short, Rogerian therapy. Third is extensive group therapy and social skills training, and lastly, the token economy system. So there were four categories, so it's a 3 by 4 categories. Now, what we're going to have is we will start with the null hypothesis. In this case, I'm no longer going to teach you the symbol because the symbol here does not matter so much. We will just write the equivalent statement. For this one, the null hypothesis is that, remember, she is testing, the psychiatrist is testing whether effective, that the state, whether the treatment or the therapy given was effective or not. In this case, that's the alternative. So that means to say the null hypothesis is the opposite. So the null hypothesis here will mention that we will say that the method, okay, the method here refers to the therapy session or the therapy provided. The method of treatment and the degree of okay, the method of treatment and the degree of improvement are independent. Okay, so we have here sorry, actually, we have the degree, the method of treatment, the type of therapies employed, and the degree of improvement, whether improved, got worse, and no change, are independent. Meaning to say, whether they receive treatment or not, their improvement or getting worse or no changes at all, they were not actually related. So it doesn't necessarily follow that if I am receiving a psychodynamic therapy, then I have the tendency to get okay. Or if I'm receiving therapy, I have the tendency to get to lessen my what's that? Schizophrenic condition. And much more that even if I receive therapy, it doesn't also guarantee that I will become more uh, schizophrenic, having a schizophrenic condition, or no changes at all. Okay? So the
Excuse me, sir.
alternative in this manner is just exactly the opposite of this. Yes.
Sir, pwede ba if ang null hypothesis ka, the before before treatments does not have a significant effect, sir?
Sorry?
Before treatments does not have a significant effect, null hypothesis. Pwede ba? Ano?
No, we cannot test because we're not testing here the treatment, whether it's effective or not. Although that is the might be the implication later on, but that is not what we're testing. What we're testing here is whether is there a significant relationship between the improvement, the condition, the degree of their schizophrenic condition, uh, and the therapy session that received. That's what we're trying to correlate here. Whether there is a significant relationship between this result. We follow?
Okay, sir.
But we're not testing whether the therapy session is effective or not. But it might be later on a leading, might be the implication, whatever is our result in here. What we're trying to test is there whether dependent where dependency took place. In other words, the degree of schizophrenic condition is related or dependent to the type of therapy session received. In other words, they are intertwined, they are related. Okay? That's our null hypothesis. So opposite to that one, they are not related. Meaning to say, in this scenario, is that we're claiming that they are related. Meaning to say, if though you are receiving the more treatment that you may take, what the tendency is that you will, it's either you become improved or you have a worsened condition of your schizophrenic condition, something like that, or no changes at all. Okay? Why the situation or the hypothesis happens to be this one? Because this is based on the situation of the problem. The psychiatrist is trying to test to treat okay, to test whether the treatment is improving lives of her patient or patients. So we have already our null hypothesis situated in this form. Then opposite to the statement is our alternative, which we intend to reject this one that they are independent so that the implication here, if this is we will be able to reject this one, we will now then claim that the condition, the degree of schizophrenic condition of the patient is related to the extensive therapy session that they receive. Did you follow? If we happen to reject this one in our test, but if not, then we don't have sufficient evidence based on the gathered data that the two categorical variable are actually related to one another. So in other words, whether I receive or not, my condition of getting worse in my schizophrenic condition does not does not I mean is not affected whether I receive whether what kind of therapy session I receive. Okay, at least its implication. Question. So step two is that we decide now our statistical test. In this case, you notice that we have three categorical data versus four categorical data. I mean, we have two data set here with three categories versus four categories. So it follows we cannot use a 2 by 2 contingency here, nor a one-way chi-square test. We can use here the two-way chi-square test as our test of statistical tests. It says that the data consists of frequencies in categories arranged along two dimensions. Two dimensions, that means to say we have two here, then two above. That the two here consists of three categories, and then the two above consists of four categories. So the appropriate statistical test here is the two-way chi-square test. And then set our alpha at 0.05. So with this one, we did already this part. We will have now our gathered data. Assuming that this is the gathered data. Okay, we have here the 80. Okay, so we have set now, assuming that this was the gathered data or the information. Next step is we will now set our rejection region, correct? Now for the rejection region, you notice that this is no longer a one-way chi-square. So since this is two-way, I'll just erase first this one. Just take note of our hypothesis. What we're going to do here is that let's have first our I'll have first the diagram. This is step 4. And then we need our DF. Our DF here is, I mentioned last time that there were two ways to get the DF. In this case, since this is already two-way chi-square, so we have C minus 1 times R minus 1. So in this case, how many columns do we have? There are 4 therapy sessions. The column 1, 2, 3, 4. So that's 4 minus 1. Then how many rows? We have improved. The improved got worse. That's also 3. So that's 3 minus 1. Giving us now 3 times 2. We have 6 is our degree of freedom. And then we set already our alpha is 0.05. What is our chi-square critical on the table? 12.59. Okay, so we will set now that one here. This is critical value of chi-square crit of 12.59. So this is our rejection region, reject, and this area here is accept. Okay, we will shade this region. So that is our intended rejection area for this test. Now we have already stated our step 4. Our step 5 is the computation. For the computation, we have already the expected value. I mean, we have already the observed value. What we need is the expected value. How do we compute the expected value? We will use this formula. Expected value is simply row sum times column sum divided by n. So for example, for the improved, to get the expected value for the improved and the psychodynamic therapy, that is simply the row sum here is 34 And then the row column is 20 divided by our n was 80 here. Okay? Our n here is 80, so that's 80. Compute that one. That is 34 times 20 divided by 80. This is only 30, right? Yeah, 20, that's why. That is 30 times 6, 30 times 20 divided by 80. I have 7 points, so this is 7.5. Okay, so in other words, my value here, I'll just put it in blue. This is 7.5. That is the this is the expected value. This is also 7.5, 7.5. That's the expected value for all the telegraphy. Next, we'll do the same for the node change. That is 28 times 20 divided by 80. That is 7. So this is, the one in blue are the expected value. Okay? And then, that is 22 times 20 divided by 80. We have 5.5. So this is 5.5, 5.5, 5.5, 5.5. Okay, we have already the expected value and then the observed frequency, the observed frequency and the expected frequency. For the solve for our chi-square computed, I'll just have to erase this one. I'll just have to remind you that our formula is chi-square is equal to the summation of FO minus FE squared divided by N, right? Sorry, divided by F sub E. So we follow that formula. So the first one is we have 6 minus 7.5 squared divided by 7.5 plus 4 minus 7.5 squared divided by 7.5 plus 8 times 8 minus 7.5 squared divided by 7.5 plus 12 minus 7.5 squared divided by 7.5. That's it. Then continue again to the next. Can you do that? What is the result? Following this formula, we have to get the summation of all for all the categories here. Did you understand how to apply this one? So it's like, after that, you have plus 6 minus 7 squared divided by 7 plus 14 minus 7 squared divided by 7 plus 3 minus 7 squared divided by 7 plus 5 5 minus 7 squared divided by 7. Then 8 plus 8 minus 5.5 squared divided by 5.5 until the last one. So what's the value? Our computed value here is actually, if you will perform the result, it is 21.4. I hope you got this value, 21.4. So we reject. Because the null hypothesis implying that the two variables, the two categorical variables are independent. Since we rejected that one, then it implies that the two variables are dependent. In other words, the degree of schizophrenic and the type of treatment are actually related based on the gathered results, since we rejected the null hypothesis implying that they're independent. So there is association going on. You follow? So the two categorical data here are actually related to one another, since we rejected the null hypothesis. Since association exists, we can now test the degree of the association. The same with Pearson coefficient, the Pearson's R coefficient, we can also find out here what is the degree of the association. That is where chi-square, or that's where the we will not use the phi coefficient, but rather we will use the Kramer's V. Kramer's V is designed to know the degree of association. Can I erase this portion here? Okay. Okay. So the degree of association using the Kramer's V, or also known as the phi Kramer's. I think phi Kramer's. Let me check first the term. Kramer's phi and the contingent coefficient. Okay, Kramer's phi or Kramer's V. The formula for this one is phi, see there, and it equals the square root of chi-square divided by n times L minus 1. Okay? Of course, this is chi-square value. This is the sample size. L here is either row or column, whichever is smaller. Okay? So we will compute now. Our chi-square value was 21.4. Our N is 80. Our L, what must be the L? You choose between the categories in the category A or category B, or rather variable A and variable B. Variable A has 3 categories. Variable B has 4 categories. So which number of categories in the two variables are we going to consider for L? Either row or columns, whichever is smaller. So we have 3 rows and 4 columns. So we're going to take the columns, rather the rows, for there are only 3 rows versus 4 columns. So our L here is 3 minus 1. So computing now this one, that's 21.4 divided by 80 times 2. Calculator is off. 21.4 divided by 80 times 2. So we have 0. What? I think my value is not correct. It should be in radical symbol. 21.4.
1.03, sir.
21.4. What's the value? We have 0.37 in 3 decimal places. 2 decimal places, that's 0.37. 0.37 is our degree of association. That's the strength, rather, the strength of the association. I will share to you who has this. Who was that earlier who sent me message? Can you send me message again? I shared to you the how to interpret the Kramer's V. I know, I'll just write it. It's here. For Kramer's V, if B is inclusive of 0.1 to 0.3, weak association. If V is 0.4 to 0.5, there is medium. Okay, medium. And then V is greater than 0.5, there is strong association. Now, if we look at our Kramer's V or our Kramer's phi here, what type of association there is? Since it's significant, what type of association do we have? This falls on the medium. There is a medium association. So between the the type of therapy session you receive, and then the degree of schizophrenic condition, it turns out that the two variables are related. They are significantly related to one another, and their strength of association is medium. But hold on, you have to understand that in an actual sense, it's like this. When I also do the statistical analysis for most of my students, when I ran it using chi-square, two-way chi-square test, if the decision is fail to reject the null, interpretation is not significant, I don't look for the strength. Because what's the point of looking for the strength of the association when it is not significant? So only we are going to look for the significant association. No, only we look for the strength of the association when our interpretation is significant and our decision is reject the null hypothesis. Take note of that. By the way, you might be wondering, sir, 0.37, where should it fall? Because this is from 0 inclusive. By the way, the bracketing here is meaning to say from 0.1 until 0.3, including the 0.3 and including 0.1. But since this one does not, 0.37 does not belong here nor here, but rather is something like this one. So if you're going to look at this value, 0.37 is way still closer to the medium association compared to the weak, because this is 0.37 closer to 40% than 30%. That's why we would now, that's why we tag this one as medium association more than weak association, because 0.37 is way closer to 40%, which is the inclusive of the medium, more than the 30%, which is in the weak. Okay, in case you are wondering.